Well, let's begin. So our second speaker before lunch is Joel Johnson from University of Texas, Austin, who will be speaking about a different title than it's in the handout, but I'm sure he'll explain why. So, Joel.
All right, thank you very much. Please do feel free to ask questions during the talk. The whole thing is, of course, for this to be about communication. I did keep on sort of adding words to the talk, and hopefully it'll give some good things to, talk about afterwards. So I'm going to present some experiments that I ran under conditions typical, when scaled up, typical of step pool streams. I have step pool in quotes just because I'm not going to directly address how well we got particular steps to form in these experiments. But I will talk about the grain size distributions of the bed and of the transported sediment, how that changes through time, how the coarsest grains end up being clustered, and finally at the very end a little bit about how one might model sediment transport when we have large changes in sediment supply. And I also threw in disequilibrium morphodynamics, and in a sense that's a little repetitive because the notion of morphodynamics, the feedbacks with sediment transport and bed topography should certainly be able to include disequilibrium conditions. But I think a big picture here is that a lot of how we think of channels and of sediment transport has an assumption, implicit or otherwise, of steady state conditions there. So the reason that I think disequilibrium matters greatly is that it's usually floods, extreme events, channel responses, not at equilibrium that really matter for people. Of course, talking about what I'll talk about. After some intro, I will describe the flume experiments. A thing to keep in mind is that I used a narrow flume, 10 centimeters wide, kind of making it as small as possible to capture what I at least wanted to or tried to get out of it. As far as results go, I'll kind of present it in three different parts. First, talking about and showing how this coarse alluvial channel bed responds when you add an idealized pulse of finer gravel to it. Basically, how does the bed change? How does it restabilize after this perturbation? And the short of it is that it gets both coarser and rougher. And the clustering of the coarsest particles on the bed also changes a little bit. And what I'm going to do with a particular clustering statistic is show, I think, that there's a bit of a trade-off between the surface grain size distribution that develops and the degree of clustering, and how they both contribute a little bit to the stabilization of the bed in these flume experiments. And finally, I will talk a little bit about reference stresses, basically not truly a threshold, but threshold-like of motion, and how that might depend on the supply of sediment to channels. So the data that I'm presenting were collected by a former master's student of mine, Alex Aronovitz. The analysis that I'm showing are things that I've done with the data since he finished. I want to acknowledge his contribution. He actually also built Flume as part of his master's thesis. Now, I did get him out into the field some as well. This photo is from the Henry Mountains of southern Utah, where I'm still doing some ongoing work. And I like it because it shows a coarse alluvial channel, lots of boulders, as well as finer sediment. Some of the boulders are organized into steps, but honestly, a lot of what you see there is a more, I would argue, random topography. And we tend to classify these mountain river systems in terms of somewhat idealized version of steps, whereas in reality, at least my perception and opinion of it, is that the topography in these systems, step pool systems, tends to be a little more variable than we give it credit for. Here's a picture of a river restoration project that admittedly has a more regular, idealized topography, perhaps one that's a little unlikely to last in that present form. And you can see kind of smaller grains making up these steps, for example. To really, yeah.
We can interrupt, yeah?
Please. Oh dear.
It says Calabasas CA, Joel Johnson.
Oh.
Does that mean you're claiming credit for that?
No, not at all. It means that I did take the photo and came upon that site. So I was just trying to say it was my photo. Sorry.
That thing is really awful.
So that's an example of a restoration project near a hotel that I was staying at one time that I found and.
You're denying that it's awful.
No, I am not taking credit for that design. My other point in showing a restoration photo like that is to say that to be able to do effective, river engineering and restoration, really you need to understand the morphodynamics of these systems, and how these engineered systems will respond to perturbations as well. Because again, with natural hazards, with floods, and also with the perceptions of humans often of nature, the times that really people think about nature, I think, is exactly disequilibrium conditions in these systems. So to zoom in on disequilibrium conditions a little bit more, what I'm really going to focus on is these experimental and idealized pulses of sediment. So disequilibrium conditions with respect to supply from upstream. And we do get supply variations that naturally occur due to events like landslides, wildfires, land use. And of course, we also use them in engineered systems, including for gravel augmentation. So let me move on to talk about the actual experimental design. This is an image of the flume that we used in these experiments. And again, it's a small flume. The length downstream of the head box is a little over 4 meters. It's narrow, it's 10 centimeters wide. And we recirculate water, but not sediment. So there's a sediment feeder. I can control the input flux and size distribution at that end, and we catch the sediment down in the tailbox. And in general, in these experiments, I want to, of course, control and then measure as much as I can. We control the water discharge, the sediment flux in and grade size distribution, and the initial slope of the bed. And as you can see, we measure the flow depth. We calculate a water velocity from flow depth and discharge. And at the downstream end, we measure the sediment flux out, sieve it to get a grain size distribution. And then within the channel, I also measure the grain size distribution of the surface using color-coded sediment, and I measure the topography of the channel bed. Here's an image showing the sediment that I actually used. There were 5 different size classes there, and the coarsest stuff was actually close to this. It had a median diameter of about 23 millimeters for that coarsest size, and the smallest size class was less than 2.8 millimeters. Surface grain size distributions during the experiment were made using image analysis such as you kind of see in that example. So in the particular experiment, I held, can't vary everything, I held water discharge constant, at a relatively low discharge. Now, I'm just actually going to present data from 4 experiments. And it was 2 runs at 8% slope, 2 runs at 12% slope. So again, steep mountain river sorts of gradients, but with one repetition each, although as I'll also show, there are some variations within these different runs that end up being interesting. So here's I'm showing time versus the flux of sediment, but also water. So again, keeping water discharge constant throughout. Now, the initial condition of these experiments was a bed of this range of grain sizes that we just put in the flume and screeded to be flat. It wasn't water worked at the beginning, so we're starting from what effectively is a unstable, rather perturbed bed state. I let the water run for a while until the bed is pretty stable. And in this case, what that means, because initially we're not feeding any sediment in, is that the sediment flux coming out has dropped to close to zero. Of course, it's never going to entirely get there, but you would let it drop by a few orders of magnitude, and that flux out becomes pretty low. Then I add a pulse of sediment, and the sediment going in is all the finest size class, so it's not the full grain size distribution that the experiments start out with. Then, finally, we stop that pulse of sediment and let the bed again restabilize until the point where the flux out has dropped substantially. So, really I'm going to be looking at the adjustment of the bed from unstable to stable kind of over that time window, and also how it responds when you increase the supply of sediment. And just some numbers for the flow conditions. Flow depth vary during the runs, but average about 2 centimeters deep. Fruit numbers average to be a little less than 1 for the experiments. So, to say what this would actually scale to, let's assume that this represents a 1/15 scaling, and basically that gets me to something similar in at least some ways to the Riacordon stepped pool channel in Italy that has been well studied. The slopes are a little lower, but still comparable. The sort of probably biggest assumption in the scaling is here, is that the width of the flume scales up to be, about a quarter of the width of the field case. And so, the flume, I'm thinking of it as representing a subsection of the actual channel, but not the entirety of the channel, which, I'm at least going to argue is reasonable for clear, straight, smooth plexiglass sidewalls. The grain size distributions, when I, of course, scale them up, would end up being something like this. And basically, the bulk D50 is fairly comparable to what you see, at least on the surface in the field, D84. The smaller size fractions are a little coarser in the experiments.
For clarity, your D50 on your flume is 6 millimeters then about? Scale of 1/15?
The bulk D50 was about 6 millimeters. Yeah. And so finally, thinking about discharge, it scales up so that the kind of constant discharge that I have for these experiments ends up being about the peak discharge of a 2-year flood. Although, a flood that had that sort of an average discharge would occur a little more rarely in the field than that peak discharge. All right, so let's look at what these experiments actually look like. See if the videos pop up in the right places. So this is certainly a sped up version. I'm going to go back to the beginning. A lot of change happens right at the beginning. And in just a moment, we're going to see a feed of finer ground sediment coming in. But you can see the flow depth ends up somewhat comparable to those largest grains. There you can see this feed of the finest size class of sediment coming into the flume. The feed has already stopped. There was some scour, happened to get down pretty low in that place. There it's repeating. So I know it changes fast, but
Clarify, is there any sediment feed when you form the bed before you put the fines in?
no. The sediment that's transported out is during that period is entirely entering from the bed. Let me show another video. So this one, what this is a series of photos taken from above where we don't have flow when the flow when the pictures are taken, but basically showing again the evolution of grain sizes on the bed. There's a feed period that just passed. It actually loops back to the beginning. A thing to note here is that the largest grains, these red grains, are definitely moving and rearranging, becoming rearranged in the flume, both initially and in part as a result of the perturbation of sediment.
Can you repeat how you prepared
Yes.
the initial bed?
Yes, sorry, I know I'm throwing a lot of things in here. The very initial bed surface was, just that we put sediment in the flume manually and smoothed it and flattened it. So it wasn't a water-worked bed.
And did you try to make it as well mixed as possible, or you didn't worry about that so much? Or?
So that's a great question. I will get to that a little bit later. We tried to make it well mixed and to have a random distribution, that represented the bulk mix at the surface at the starts of the experiments. There was some variations in that initial surface grain size distribution, and really because it's so hard to avoid basic kinetic sieving and to get it to have a representative surface size that matches the bulk. But we at least tried to have it be a consistent initial topography.
One more question.
Yeah.
Can you explain how did you create the sediment pools? Was kind of dumping, because I'm not familiar with this.
Yes, okay, so
sediment or just was dissolved, with suspension, and then.
Yeah, so the sediment pulse we did by using a sediment feeder. Let me just hop back to there. We'll see, I thought it was going to be worth it to go back to there. So this is actually a sediment feeder. There's a tube here that brings sediment that comes out of there down into the flume. And so you basically set the feeder to feed in the sediment at a controlled rate. That is dry sediment that's coming in. Though it's coarse enough that it sinks right to the bed at the beginning and does move through its bed load. Yeah. All right. Actually, let me go back to one other thing. The data that I'm going to show next, I'm going to, show both, first transported sediments in terms of the flux out of the flume and the grain size distribution. Then I'll show how the bed roughness evolves, how the related hydraulic roughness evolves during the experiments, and finally we'll show some results on the clustering of the coarsest grains. So here is a plot. There's runtime versus sediment flux, and the red line is the flux in. I have zero flux here at the bottom, though the rest of these scales is a log scale. Just note that. And initially, starting from this unstable bed, we have a very high sediment flux, which drops off rapidly and then more gradually. I am stopping the flume to make various measurements, and we get down to this level of 1 to a few grams per minute coming out of the flume, and it doesn't